Hi everybody, this is Mr. Folly, and welcome to podcast 4.4. We're going to talk about how metals conduct heat and electricity, long chain polymers are flexible, pharmaceuticals have specific shapes, and bond energy equals K Q1 Q2 over R squared. Alright, so a little function. A little bond energy, and that's about it. So let's hop to it. Oh, come on, hop to it. Metallic properties are due to their structure. So if I have malleability, like this right here, malleability, why are metals malleable? Because they're, and we talked about this, their electron C, or their non-directional covalent bonds, allow the metals to move around a lot more. See how this space is a little bit more? So why are they malleable? Because non-directional bonds, see how I'm doing this? Non-directional bonds allow movement. Now I say that, but what is the other choice? And the other choice is a lattice. So we talked about how network covalent bonds are outrageously strong. And remember, this would be three-dimensional. I can't break this. There's not movement available here. Okay? So positive charged ions due to nuclear. This shows a flow of electricity. So this shows why it conducts. This is still a metal. Conducts electricity. Remember, electricity is a flow of ions. Right? So if the electrons are able to flow, look at how they're flowing right there, they're conducting electricity. So they're delocalized, meaning they are allowed to flow all over the place. So they can conduct electricity. Another example of conducting electricity, because they can flow. So if I jam a big negative charge right here, it will push the negatives that way. A polymer's flexibility is due to its structure. The long chains can fold on each other due to attractions in other spots. So this is a flexible polymer. I was looking at a flag football belt. Oh yeah, look at the amazing parts of, boy, this is not going to work at all. A flag football belt has this clip where this part jams in and it fits in here. I should have actually got a Google picture of that to do it. But it bends in and then it snaps. So any snap or buckle, like your buckles for your backpacks, those need to flex and still have some strength. That's because they're very long and they can fold, and there are attractions here. And these attractions here, notice they're not real bonds. They're strong intermolecular forces. And remember, the intermolecular forces mean that they're weak, which means that they are breakable. But it also means that they are reformable. Oh, so if it is able to be broken and reformed, that means it's flexible. Oh, I see. So intermolecular forces allow something to break and reform. Pharmaceuticals, that's drugs, have a structure that is designed to interact with a specific part of the body. It's a drug. Notice how the tight-fitting compound will either do what the purine nucleoside does, or will keep out the purine nucleoside. So here's a purine, here's the purine nucleoside, right? So if this is the bonding site right here, and you have a drug that does this, like, oh, then that will have the same type of deal. So if this is good for the body, or whatever it is, this drug will be good for the body. If this is bad for the body, this will keep that bad stuff out, right? So it can be competitive inhibition. So again, this is idealized. Molecules don't look like that. What is closer to reality is this look. The stick in the middle will bond H bond or other intermolecular force. So here's the stick. Here, see the stick? Whee! Okay, that will bond H bond or intermolecular force in a site that will activate or deactivate the molecules. This is typically a protein. So again, we have intermolecular forces, and the beauty of an intermolecular force is it can break and reform. So if it can break and reform, that means, I mean, you may want some aspirin to be a painkiller, but you don't want painkillers all the time. Sometimes it's good to feel pain. We call that pain health class. Oh, I made a joke about health class. What makes these bonds stick anyway? It's Coulomb's law. Now, Coulomb's law is based on the fact that positives love them some negatives. Positives love them some negatives. And negatives love them some positives. And then we find out that negatives hate negatives and positives hate positives. I suppose I should keep that up. Okay. Bond energy is some constant K. Whoa! Some constant K times Q1, Q2 over R squared. And frequently you see this as Q1, Q2 over D squared. But R is the radius of the atom, or D is the distance. I see both of them depending on what book you use. So K, Q1, Q2 over R squared. The 1 just means charge number 1 and charge number 2. So notice if they're positive and negative, that means there'll be an attraction, and my bond energy will be negative. So negative bond energy forms bonds. Forms bonds. So again, instead of a dash, I'll make that negative bond energy forms bonds. Okay, and those are listed. So how do we use this, you ask? Okay, so Coulomb's law. So that means if I have these charges right here, and I have a +2 and a -2, that would be -4, right? That would be stronger than if I had a +1 and a -1. That would be -1, right? So bigger charges means bigger bond energy. All right? So change those charges in a segment. And smaller is stronger. So R is the radius, right? So if I have, let's just say this term right here. So if bond energy equals 100, and my radius squared, let's say my radius squared is 25. Come back. Is 25. Or I have come back here. Or I have a bond energy where I have 100 divided by 15. Which one's bigger? Oh, come back. Oh, stop that. Which one's bigger? Well, the one with the smaller radius will give you a bigger bond energy. This is 4. This is more than 4. Yeah, I'm not going to add it up either. Why is a dipole weaker than ionic? Oh, do I have an eraser choice here? Oh, eraser. Boom. I don't have an eraser choice. Great. So why is dipole weaker than ionic? Remember, dipole are the... So why is dipole weaker than ionic? Remember how dipole has to deal with temporary and small forces. So if I have a full positive and a full negative, why did I put -2? I don't know. And a full negative, or I have positive 0.03, that's a delta, right? Delta positive, just a little bit. Delta negative, negative 0.11, it's going to be a lot smaller. All right? So why is dipole weaker? The charges are a lot less. How can the bond length be shorter? Why is triple shorter than single? Well, they pull in more. Triple pulls in more. Bond S, so if I'm bonding to S, or I'm bonding to O, back here, I'm bonding to S or I'm bonding to O, which one would be shorter? Well, remember, these guys are small, and down here, they are big. Remember how I have small, and I keep adding energy levels, right? So which one's going to be shorter? Bond to oxygen is shorter, right? So if the bond to oxygen is shorter, then the bond to oxygen is stronger, right? Because I'd be dividing it by a smaller number. And this F we'll call bond energy. Okay. What bond has a higher bond energy? BAF2 or BACL2? Oh man, I meant to put well, let's do this. Bond energy equals, I'm not even going to put the K's there because it doesn't matter. Q1, Q2 over radius squared. Well, Q1 is 2, right, plus 2. Q2 is -1. So notice, even though I have 2 of them, it's -1 over radius squared. Oh. Plus 2, -1 over, I'm going to call this Y. Whee! So if I look, I've got to look at chloride or fluoride. Chloride and fluoride. See how fluoride is smaller? So if fluoride is smaller, then fluoride would be stronger. Right? Smaller equals smaller. Higher bond energy would be BAF2. BAF2 because same charges and F is smaller than Cl, which would have a higher melting point. A higher melting point would be the one with the stronger bonds. Remember? Which one has stronger bonds? Well, we just said it's BAF2. NaCl is stronger than NaBr. Here's Cl. I wish you could get rid of this. Here's Br. Why? Cl is smaller. So in bond energy equals K Q1 Q2 over R squared. The smaller bond is stronger. There you go. And there you go. Metallic properties are based upon their structure, specifically loosely held electrons and flexibility. Polymers are flexible because their chains are so long they can fold upon themselves and break and form intermolecular forces easily. Notice inter forces easily. Chemists design drugs to attack specific sites to change the structure of another molecule. Size and charge determines damage. So that is it. Toodles!